So I begin?
Let me introduce you. Okay.
Okay, thank you.
Welcome back, everyone. Today we have Yilin Wu, and he's going to tell us about relative cluster categories and Higgs categories. Thank you, Yilin.
First, I would like to thank the organizers for the invitation. Today, I will talk about the relative cluster category and the Higgs category with infinite dimensional morphism space. So the plan of today's talk has three parts. First, I will talk about cluster algebras and cluster categories. And then I will introduce the relative cluster category and the Higgs categories. And the third part, I will introduce the cluster characters. Okay, let me go to the first part. First, let Q be a finite quiver without loops or two cycle. And then by definition, the associated cluster algebra is a commutative Q algebra endowed with is a commutative Q algebra endowed with a distinguished set of generators. This is called the cluster variables. And then those cluster variables are grouped into a subset of fixed size. Those subsets are called clusters. And then the cluster algebra are constructed recursively from the quiver Q using iterated seed mutation. Let me introduce, if Q0 is the vertex set is indexed by 1 n, and then the AQ is a subalgebra of the function field. Generated by our cluster variables. More generally, a cluster algebra with coefficient is associated with an S-quiver. Here, an S-quiver is just a finite quiver with a frozen subquiver. Let me introduce some examples. The first simple example is just we consider the quiver Q, just two vertices with an arrow A2 quiver. Then we have the cluster rebels. With 5 elements. This example is, with no has no coefficient, and then we consider the second one is from Lie theory. Consider the unipotent matrix where A, B, C are complex number. This is Lie type A2. Consider the following functions. Functions on N. First, X takes a matrix to be this determinant. So S is just equal to A, and the X prime takes M to be the determinant at 1, 2, and 3. This is equal to C. And another one is take the matrix to this determinant. So this is just the AC minus B. The last one is takes M to determinant at 1 and 3. This is equal to B. So consider the 4 functions, then the coordinate ring of N is generated by these four functions. With relation x prime equal to y plus z. In this case, this zero-associated quiver is a S quiver. Here we'll put y and z, and another one is we'll put the rebel x. So in this case, the cluster rebel has 4 elements. And in this case, this cluster type A1. More interesting examples come from Grassmannians. Consider the coordinate ring of Grassmannians. Here is the affine cone. In this simple case GR24, we have this following as quiver. This is a special case of the work of Scott. So this is the definition of causal algebras, and then there we consider the additive categorification. Rough idea is just we find a triangular category C with a decategorification map. Namely the causal character from the object of C up to isomorphism from to the causal algebra. And this map satisfies following properties. The first one takes a decomposable rigid object of C up to isomorphism. It takes the rigid objects to the causal rebels. And the second property is takes the basic causal tilting objects. Of C, it maps to the cluster clusters. For example, if T decomposes to n direct summons, it maps to these clusters. And this kind of category are constructed by following works. The first case is the acyclic quiver for C is for if the causal algebra comes from acyclic quiver, then this category constructed by Buan-Marsh-Reineke-Reiten-Todorov. In 2006, this for acyclic quiver. And then the causal character for CQ is constructed by Jacobi-Finite formula by their work. Also in 2006, more generally, for quiver with potential is constructed by Amiot in 2009. She considered the Jacobi-finite case. And in this case, the cluster character is introduced by Dixon, Wellman, Zelwinski, and Palu. Later, for the Jacobi-infinite case, the category is considered by Plamondon in 2011. We consider any quiver with potential. In particular, for the Jacobi-infinite case. And he also constructed the cluster character. These three categorification are for cluster algebra without coefficient. For cluster, if the quiver Q comes from the Lie theory, then there is a coefficient in the cluster algebra. Then the category C is a Frobenius category. Or it is stable category. And this Frobenius category is contained in the module category of pre-project algebra. This construction is due to Geiss-Leclerc and Schr&ouml in their several papers. So the aim of this talk is to generalize the 2, 3, and 4 to any S quiver with potential. And then the category C is replaced by Frobenius X triangular category, namely the Higgs category. So let me go to the second part, the relative cluster category and the Higgs category. To construct these two categories, we need to first define the relative Ginsburg algebras. So let K be a field, algebraic closed, and with a character 0. Let Q F be S quiver. Just so F is the subquiver of Q. Let W be a potential on Q. That is an element in the zeros Hochschild homology in the path algebra. For example, in this simple example, we take the W to be the 3 cycle. And the second example, we consider the example as pairs. So in this example, we take the potential to be the alternate, the sum of this kind of 2 cycle minus another orientation. For example, in here, the sign is minus, this plus, minus, plus. So if we have S quiver with the potential, we can define we will define the complete relative Ginsburg algebra. And the complete 2-carbon completion of the frozen part. And both those two algebra are completely path algebra, DG path algebra. For example, if we consider the first example here, so we have the following two digit algebras. For the construction of two caveat completion, we first take the original quiver, is this frozen part, and then for each arrow we add an opposite arrow of degree 0. We check degree 0. And for any vertex, we'll add a degree -1 loop. This is degree -1. And then we define the differential. So in this case, B check is degree 0, and 2, 3 is degree -1. And we have the differential. For the degree element, the differential is just 0. And for the degree -1, for example, ds2 is just minus B check B. ds1 is the B check. So this is the two caveat completion of the frozen part. And then we also have this complete relative algebra. First, we take the original quiver. And then for each unfrozen arrow, for example, these two arrows are unfrozen. Unfrozen arrow, we add an opposite arrow degree -1. For each unfrozen vertex, for example, this vertex is unfrozen, then we add a loop of degree -2.
Sorry, the right arrow should be C.
Oh, yes, thank you. So then we define the differential for B, C. For the degree -1 arrow, for example, this differential is defined by partial derivation with respect to the potential. For example, the potential is ACB, so it's just the partial derivation of A is a CB, and the differential at C star is partial differential at C is just BA. And for the degree -2 loop is given by this kind of 2 cycle. So moreover, we also these two DG algebra are related by DG functor. This is the first example, and then let me give the second example. So in the first example, in particular, this example, this DG algebra is concentrated in degree 0. And in this algebra is not concentrated in degree 0 because this is thinking type, A2 type. So this is not concentrated in degree 0. And in the second example, we consider this Grassmannian, this quiver. So first we have this two Cabell completion. This is two Cabell completion because the original quiver is no Dinkin, so this algebra is concentrated in degree 0. And we also have this relative Ginsburg algebra. For each unfrozen arrow, we add opposite arrow degree -1. And there are only one no frozen vertex. We also add a loop here. We also have a DG functor. And then moreover, in this example, this is also concentrated in degree 0. So we have constructed a DG functor between two DG algebras, where we have the following remark. So this DG functor G, it is a relative 3 deformed relative 3 Cabell completion of a DG of a inclusion. It is the relative deformed 3 Cabell completion of this DG inclusion with respect to the potential. So this is due to Young in 2016. If it is a relative 3 Cabell completion, then by Bruhat by Young's result, it has G has a canonical 3 Cabell structure. In the sense of Bruhat in 2019. We say S quiver with potential is Jacobi-finite, a relative Jacobi-finite. If the relative Jacobian algebra is finite dimensional, otherwise, we say it is a Jacobian infinite. relative Jacobian infinite. For a DG algebra A, we denote by DA, the derived category of A. Is just the localization of the GGA module respect to the quasi-isomorphism. In this unbounded derived category, we have a perfect derived category, perfect A. Is defined by the six subcategory generated by A over itself. And we also have the finite dimension, perfectly valued derived category. This is just the object in DA. Its total dimension is finite. In other words, it's just to say as K module is perfect. Then we can define if A is smooth, we'll say A is smooth. If A is as a bimodal is perfect. For example, the two DG algebra we constructed are smooth. If you have smooth DG algebra, then you can get perfect valued derived category is a subcategory in the perfect derived category of A. So now we can define what's the relative cluster category. Is defined as the idempotent competition of the following triangular quotient. Where this subcategory is defined as a subcategory in the perfect valued derived category of gamma relative. So this is defined by object in the perfect valued derived category such that M restrict to the frozen part is 0, where E is or the sum of our frozen idempotent. So in other words, this category is generated by the simple module in the unfrozen part. The six subcategory. We have this kind of category, then we define the two subcategories in the perfect derived category. This is let present category. Just the name of presentation by the gamma relative, but it has some condition on the frozen part. Is a cone of S1 to S0, where Si is in the ADD gamma relative. And we also have this condition. This map F satisfies the following extension property for any object I in the edit closure of E gamma relative. Just means this object has a property of injective objects. Dually, we define the co-present category. The shift cone and this object also in the ADD gamma relative. We also satisfy these dual properties. For each object, P also in this additive category. So this means this object in this subcategory has a property of predictive property. And then we have the following proposition. Because in the definition of the relative cluster category, we have this canonical quotient. So these two subcategories are subcategory in the perfect derived category. Consider this canonical quotient. Then we have the restriction on these two subcategories is fully faithful. So we can define the Higgs category. The Higgs category is defined as a subcategory in the relative cluster category. It's just M in the image of these two intersections. So M is in this category, and M also satisfies these finite dimensional properties. Is finite dimensional as a relative Jacobian algebras over so this is the definition for the Higgs category. And then we have the following theorem. The Higgs category is an extension closed subcategory in the relative cluster category. It becomes an X triangular category. In the sense of Nakaoka-Palu. In 2019. So, and then we also have the following, because because we also have the following isomorphism, equivalence. Here the P is, here P is just the addict closure of this DG module. And this category is defined by Plamondon. If Q bar W bar is Jacobi-finite, then this is just the cluster category defined by Amiot. Where Q bar is just we delay the frozen part. We just delay the frozen part. And then we have this third result. If Q bar W bar is Jacobi-finite, and then the Higgs category is a Frobenius X triangle category. With the projective injective objects P just equal to the closure of this DG module. And the fourth result is even moreover. This is concentrated in degree 0. I mean, as quasi-isomorphic to the zeroth homology. And then H is Frobenius exact category. And we also have this equivalence. Gaussian project module over algebra B. Here the definition is just the object in the mode B. Here mode B is a finally presented B module. And it also satisfies this extension vanish property. So this extension is computed in the big module, big B module, where B is just the boundary algebra. For example, for the previous example, in this example, this algebra satisfies this example. This is concentrated in degree 0, and also it is not Noetherian. So in this example, this Higgs category is isomorphic to the Euro-Gaussian project module. Moreover, we also have more examples are considered by Prisma. For example, if this S-quiver is comes from the Poisson diagram, then we also have the same properties. So let me go to the last part, the cluster character. So let QFW as before, S-quiver with potential. And then we have this relative Ginsburg algebra. And we also have this Ginsburg algebra. We also have this category, Higgs category, comes from a full subcategory P. Then suppose the Q0 is given by the following vertex, where the frozen part is given by the last element. Let CC is the cluster character defined by Plamondon. This is defined by Plamondon in 2011. We identify K0, the quotient group, with Gm. Then we define the following map. H can be embedded into the perfect derived category. And then we take the K0. And then we consider the frozen part. The frozen part is the last n minus elements. Then we have this composition. The composition is denoted by G frozen. So we have considered the following diagram. H is embedded into the sixth subcategory generated by P and generated by the P, the shifted by P and the Higgs category. We also have this map. And then this is the quotient. This is equivalent to the cluster category defined by Plamondon. And he also defined the cluster character. This map is specified all the xi to 0 for I bigger than n plus 1. And so consider the following diagram. Then we have the following theorem. There is a unique map CC from this sig category to this ring, such that one for each object S in H without no zero direct sum in P, we have CCX is just the X, and the first evaluate the this frozen map. Then product with this cluster, this defined by this map. And then for any p in the subcategory generator P, we have this P is just the monomial determined by this object. And the last result is for each triangular P to E to M, where the P is in the subcategory generator of P. We have this equality. So I stop here. Thank you.
Let's thank Yilin for this nice talk. I will first ask people in the room if they have questions. Matthew has a question.
Hi, thanks for the talk.
Yes, thank you.
When you were talking about the case that the relative Ginzburg algebra is formal, if it's concentrated in degree 0,
Yes.
if it's concentrated in degree 0 but not Noetherian, is the claim
Yes.
that this modified category of Gorenstein projectives is?
Yes, in this case.
This is Frobenius and stably Calabi-Yau, and it's always that you take finitely presented B modules.
Yes.
And not anything more. So is the claim that the zero thermology is always coherent, even with no for any quiver with potential? Or
in general, I don't know whether it's coherent.
Okay.
For example, maybe the example coming from your result is Noetherian, so it's coherent.
Well, I have more examples where I don't know if they're the Noetherian, and probably they aren't. So that's why I'm asking.
Okay.
Okay, that's good.
Thank you.
Any other questions from the people in the room? I don't see any in the room. What about Zoom audience? Are there any questions?
Hello, hi, can you hear me?
Yes.
Yes, perfect, thanks. So thanks for the talk. I have a question. Can you say what kind of Calabi-Yau structures this Higgs category has?
Which category?
The Higgs category. Does it have a kind of Calabi-Yau property?
For example, in this case, let me see. For example, you consider in this case, yes, the Higgs category is just the module over the pre-produced algebra of A2 quiver. So the stable category is as A2 Calabi-Yau, yes.
So there will always be an associated stable category, and this will be 2 Calabi-Yau.
If this is a QFW is a Jacobi-finite, then it is 2 Calabi-Yau. But in general, it's stable category is just this category defined by Plamondon. This is small category in the cluster categories.
It's only subcategory. So you're saying that the non-relative cluster category is then only a subcategory. That's what you're saying?
The Jacobian infinite, is a subcategory in the cluster category.
Aha, interesting. Okay, thanks.
Any other questions or comments?
I have one more question, if that's okay. So can you also say what kind of cluster tilting objects you get?
It's just the canonical one is just this object.
Mm-hmm. And how does it work? You have an X-triangulated category. How does does the usual technology of cluster tilting with the mutation, does it work also in that setting?
Yeah, it is our work for this object. It works, I think.
Mm-hmm. Okay, thanks.
Thank you. Any other questions or comments? Let's thank Yilin again then.
Thank you.